Okay, so welcome to this next video in which we are discussing defects in excitation contraction coupling in pathological cardiac hypertrophy. Okay, so we've seen how in cardiomyocytes which have undergone pathological cardiac hypertrophy, the type 2 ranitidine receptors sporadically open without any sort of a calcium signal. Okay, so we want to discuss the cause of this, and basically what you find is that the type 2 ranitidine receptors are over-phosphorylated in cardiomyocytes which have undergone hypertrophy. Okay, so now what I'm going to present to you is a potential reason for why this over-phosphorylation leads to these channels opening sporadically. Okay, so this is still controversial, but it is an argument that may well have some weight. Well, at least it does carry some weight, but it is still controversial, and some people totally disagree with this. But I will present it to you because it is an argument that has some weight. Okay, right, so what happens is usually when the type 2 ranitidine receptor is not over-phosphorylated, it has certain proteins associated with it. So the reason I showed you the tetrameric structure of the type 2 ranitidine receptors so that I can now do this discussion here. So basically each one of these 4 subunits of the type 2 ranitidine receptor can have another protein bound to it. So I'll draw this happening for one of these 4 subunits, but basically it will happen to all 4 of them. So basically, each subunit of the type 2 ranitidine receptor will have this additional protein bound to it, which I'm drawing now in pink here. Okay, and this protein can be one of 2 proteins. So there are 2 proteins which can bind to a subunit of the type 2 ranitidine receptor like this. And they are the FKBP12.6, okay, FKBP12.6, and also just the FKBP12. So there are these 2 proteins which can bind to the type 2 ranitidine receptor like this. So FKBP12.6 and FKBP12. Now these also confusingly have other names. So FKBP12.6 is known as calstabin 1. Okay, and FKBP12 is known as calstabin 2. Nice and sensibly. Okay, so there are these 2 proteins which can bind to a subunit of the type 2 ranitidine receptor. So I want to stress that all 4 of these will have one of these proteins bound to them. And it's a case of you can have this one or this one. It's not a case of you have both. It's one or the other. But pretty much they do the same thing. Calstabin 1 and calstabin 2 are doing the same thing, but they are separate proteins. Okay, now basically what over-phosphorylation of the type 2 ranitidine receptor causes is it causes the dissociation of FKBP12.6 and FKBP12 from the subunits of the type 2 ranitidine receptor. So basically when you over-phosphorylate this type 2 ranitidine receptor, potentially by protein kinase A, we think it's most likely protein kinase A, which is why I showed you this pathway, then the type 2 ranitidine receptor has these, the FKBP12.6 and FKBP12, they dissociate from the subunits of the type 2 ranitidine receptor, so it becomes bare again. And when these calstabin proteins dissociate from the type 2 ranitidine receptor, what this results in is a vast increase in something known as the P0, okay, of the receptor. And P0 means the open probability of the receptor. So basically, any ion channel like the type 2 ranitidine receptor always has a certain probability that it will be open. Even if no calcium is bound to it, there's still some probability that it will be open. And this is known as the open probability. So you need to be careful, because open probability, people will modify it. So they might say the open probability when calcium is bound to it, and that will be different to the open probability when calcium is not bound to it. So in different states, the protein will have differing open probabilities. Now we're talking about the open probability when the type 2 ranitidine receptor has no calcium bound to it. So basically, the open probability in that state is increased hugely in response to the calstabin proteins dissociating. So when these dissociate, this thing's probability of being open, even though it's not being stimulated by calcium sparklets, increases. And that is why you get these sporadic calcium sparks in these hypertrophied cardiomyocytes, or at least this is a theory as to why you get these sporadic calcium sparks in cardiomyocytes which have undergone concentric hypertrophy, because the type 2 ranitidine receptors now have a significantly higher probability of being open even when there is no calcium sparklet to stimulate them, and therefore when they open, they'll cause a calcium spark, and that was not triggered by an action potential or not associated with an action potential. So it was a sporadic calcium sparklet. So that is a theory, at least, as to why you have these too high levels of sporadic calcium sparks. Okay, so I just want to give one more little correlate to all of this, which is, how do we know that the type 2 ranitidine receptors are overphosphorylated in hypertrophied cardiomyocytes? So basically what you can do is you can extract the type 2 ranitidine receptors from your concentrically hypertrophied cardiomyocyte. What you can then do is mix them with protein kinase A enzymes, okay? So you take your... I'm going to get another piece of paper for this rather than attempting to squeeze it all on there. Okay, so what you'll do is you'll take your type 2 ranitidine receptor here, okay? You'll mix it with protein kinase A, okay? You'll also mix it with cyclic AMP, so that you've actually activated the protein kinase A. So the catalytic subunits of the protein kinase A have now dissociated from the regulatory subunits, and they're now active, okay? And what's the final thing that the catalytic subunits need in order to actually add phosphate groups onto this type 2 ranitidine receptor? Well, basically, they need ATP. So this is the clever part. What you now do is you put radioactively labeled ATP. Okay, so let me discuss with you the structure of ATP. So ATP stands for adenosine triphosphate. Now, adenosine means the adenine organic base bound to the ribose sugar. So this is the ribose sugar. And this box with an A in, this represents the adenine organic base. Now, this whole structure, adenine with a ribose, is what's known as adenosine. So ribose plus adenine makes adenosine. Okay, so ATP is adenosine triphosphate. So then what you do is you stick 3 phosphate groups off the 5th carbon of the ribose sugar. So let me colour this in. In blue you have the ribose sugar here. Then in red you have the phosphate groups of the ATP molecule. And then in green you have the adenine organic base. Okay, right. So what you're going to do is radioactively label this phosphate group, this gamma phosphate group here. So you're going to radioactively label this gamma phosphate. Well, the reality is you'll end up radioactively labeling them all, but the gamma phosphate is the one that's going to be important for protein kinase A labeling. Okay, so this is going to be radio labeled. Okay, now what's going to happen is when we mix this ATP with the catalytic subunits which are active, then they're going to chop off this gamma or terminal phosphate of ATP and stick it onto the type 2 ranitidine receptor. And they will phosphorylate all sites on the type 2 ranitidine receptor which are free. Now, what you do is you take type 2 ranitidine receptors from a normal cardiomyocyte, and you also take type 2 ranitidine receptors from the concentrically hypertrophied cardiomyocytes, and you do this experiment. Now, which one do you think is going to show the greater reactivity at the end of it? Okay, so let's have over here, this is the normal, or often referred to as the wild type in scientific papers. And over here, let's say this is the concentrically hypertrophied type. Which is going to be more radioactive at the end of it? Well, it's going to be the normal one. Why? Because the normal one is going to have more available phosphate groups for the catalytic subunit to phosphorylate, basically, because it's got a lower level of phosphorylation already, and therefore it's got more free phosphate groups. So let me explain this better. So we know that this concentrically hypertrophied, and I'm doing awfully spelling here, hypertrophied type 2 ranitidine receptor, I told you that it's overphosphorylated. I'm now going through the explanation of how we know that, but I told you it's overphosphorylated, which means that loads of the phosphorylation sites are already phosphorylated, and that means that they won't be phosphorylated by the catalytic subunit of protein kinase A, and therefore they won't get the radioactively labeled phosphate groups added onto them. So these ones will have far fewer radioactively labeled phosphate groups put on them, whereas the normal type will have much lower pre-phosphorylation because they aren't overphosphorylated, so they'll have far more sites that can be phosphorylated exposed on them, and that will therefore have radioactively labeled phosphate groups added onto them. Okay, so the normal type 2 ranitidine receptor will be phosphorylated much more in this experiment, and therefore will be far more radioactive than the type 2 ranitidine receptor from our hypertrophied cardiomyocyte. And that showed us that the type 2 ranitidine receptor from the hypertrophied cardiomyocyte must be already overphosphorylated, because that's the only reason, well, it's not the only reason, but it's the most likely reason for why it's not being phosphorylated by these catalytic subunits now, which is, and that simple reason is because all of its sites are already phosphorylated. So, basically, to review everything, what we have found is that in cardiac hypertrophy, what happens is the ability of the myocardiocytes to contract goes down, and this is, well, the ability of the cardiomyocytes to generate force goes down, and this is because, well, it appears to be because the size of the calcium spikes within the cytoplasm of those cells are reduced. Okay, and the reason for this reduction is firstly due to the fact that there is lower calcium stored in the intracellular sarcoplasmic reticular stores because of the reduction in function of SERCA2. Okay, that means that when you actually activate the stores to release calcium, you're going to release less calcium, and therefore you're going to recruit less sarcomeres into contracting, and therefore generate a lower amount of force. Okay. In addition, what we see is that the size of the dyadic clefts are reduced. This means that the ability of the calcium sparklets to actually cause the release of calcium from the type 2 ranitidine receptors is going to be reduced. Okay, so the size of the calcium sparks is going to go down. Finally, we also saw that you got T-tubular atrophy, which led to some of the calcium synapses just no longer existing, so that they weren't going to ever release calcium sparks in response to an action potential, simply because they're not juxtaposed with an L-type voltage-gated calcium channel, which will allow the calcium sparklet in, which is what's going to trigger the opening of the type 2 ranitidine receptors. So that's going to lead to fewer calcium synapses within the cardiomyocyte, and therefore fewer calcium sparks upon an action potential, and therefore a smaller calcium tide. Okay, and finally, we also saw the explanation, or a potential explanation, for why you get these sporadic calcium sparks within hypertrophied cardiomyocytes, which is that the type 2 ranitidine receptors are overphosphorylated in hypertrophied cardiomyocytes, and this is going to lead to the dissociation of calstabin 1 or calstabin 2, also known as FKBP 12.6 and FKBP 12 respectively, and this seems to lead to the type 2 ranitidine receptor having a greater P0 or open probability even when there's no calcium bound, so the chance that the receptor will just open spontaneously goes up. Okay, so that seems to be the defects that we see in cardiomyocytes which have undergone hypertrophy.